Change one number inside an atom and you change everything. Add a proton to carbon and it becomes nitrogen, a different element entirely. The atom is mostly empty space, with a tiny, dense, positive nucleus and a blur of electrons around it. Yet that arrangement decides every chemical property there is. This unit reads the atom like an instruction manual. We meet the three particles, see how isotopes differ, weigh atoms with a mass spectrometer, map where electrons actually live, and finally rip electrons off one by one to expose the structure underneath. Everything in chemistry starts right here. First, the cast. Protons are positive and live in the nucleus. Neutrons are neutral and sit beside them. Electrons are negative and orbit outside. Protons and neutrons are heavyweights, each about 1 unit of mass. The electron is almost weightless, nearly 2,000 times lighter, so it adds charge but barely any mass. Two numbers capture it all. The proton number, bottom left, is the element's identity card. It never changes without changing the element. The nucleon number, top left, counts protons plus neutrons, the atom's mass. A neutral atom has equal protons and electrons. Knowing these two, you can read off every particle in the atom. Next stop, isotopes. Keep the proton number fixed but change the neutrons, and you get isotopes, same element, different mass. Chlorine-35 and chlorine-37 both have 17 protons, so both are unmistakably chlorine. One simply carries 2 extra neutrons. Same identity, different weight. Here's the payoff. Because their electrons are identical, isotopes react chemically in exactly the same way. Neutrons add mass, not chemistry. So the only difference you can measure is weight, which is precisely the door that mass spectrometry walks through. Chemistry lives in the electrons. Isotopes only touch the nucleus. So how do we weigh a single atom? Mass spectrometry. The sample is vaporized, ionized into positive ions, accelerated, and then deflected by a magnetic field. Light ions bend a lot, heavy ions barely bend, so the machine sorts them by mass and counts how many of each arrive. Out comes a spectrum of peaks. Each peak's position is the mass. Its height is the abundance, how common that isotope is. Chlorine shows 2 peaks, a tall one at 35, 3 times as abundant, and a shorter one at 37. Take the weighted average of those, and you land on 35.5, the relative atomic mass straight off the graph. Now the electrons. They don't loop in neat planetary rings, they occupy orbitals, regions where an electron is most likely to be found. The s orbital is a simple sphere. Each p orbital is a dumbbell pointing along one axis. Orbitals group into subshells and subshells into shells, filling from the inside out. Electrons fill lowest energy first, and each orbital holds at most 2. Sodium's 11 electrons go, 2 in 1s, 2 in 2s, 6 in 2p, and the last lonely electron in 3s. We write that 1s2, 2s2, 2p6, 3s1. That final outer electron is the one that does sodium's chemistry. Last stop, ionization energy, the energy to tear one electron clean off a gaseous atom. Remove them one at a time, and the energies tell a story. The first few come off relatively easily, then suddenly one demands far more. That jump is the fingerprint of an electron shell ending and the next, closer one beginning. 2 clear trends to take away. Across a period, ionization energy generally rises, the growing nuclear charge grips electrons tighter. Down a group it falls, outer electrons sit further out and shielded, so they leave more easily. Those big jumps confirm the shell structure we just drew, the atom's whole logic exposed. Here's the atom on one page. On the left, the structure, 3 particles, 2 defining numbers, and isotopes that change mass but not chemistry. On the right, the 2 big tools, mass spectrometry to weigh and count isotopes, and electron configuration to place every electron in its orbital. Your drill, read the 2 numbers to count every particle, build any configuration by filling lowest energy first, and read an ionization energy graph for the telltale jumps. The shapes of orbitals in fine detail, and bonding between atoms, come in the next units. For now, you can read any atom cold.